Okay, so we're going to do Chapter 11 review today, and we're going to go through problems that are going to be similar to your test problems. I've pulled these all from the Chapter 11 extra problems that you can get off of the website. They're probably also linked on Google Classroom on the chapter help slides. We're going to work through the problems that I've listed right there, the ones that say try it pages, or where I'm going to leave it blank in case you want to go back and try it again and see if you can still copy what we did. Okay? Oh, everything's not working. Alright, so this would be a try page. I'm going to leave this one blank in case you wanted to come back and try these again. So the first one we're going to do is the HCl and the NH3. So, alright, so HCl plus NH3, they give you the reactants. That's what those two are. They want a reaction, so we're going to combine these in some way. This is an acid-base chapter, so we're looking for the acid and the base. Well, here's an H right here. It's going to run this way, which means this is our acid, or our H plus donor, and this is our base. I'm pretty sure NH3 is one of the ones in the book that you're supposed to just know that's a base. So the Cl is going to be left by itself, and this will become NH4, and because the thing that ran over here was an H plus, this now has a plus charge. Now, to finish balancing this, you have to know, are these things correct? Well, Cl is one of our diatomic elements, so it has to have a 2 there. And then NH4 plus is fine like it is. So then we have to look. All right, there's 2 Cl's on the right, so let's add 2 Cl's on the left. We now have 3 H's here, and we have 2 H's before that. That makes 5. So we don't have quite enough H's to fix this. So let's just add another 2 here and see what happens. So if we add a 2 here, we now have 8 H's on this side. But the other side, I suppose I could probably line up my little things so you could see. Alright, so on the left, I have 2 plus 3. And on the right, I have 2 times 4, which is 8. I have 2 Cl's, I have 2 Cl's, I have 1 N, I now have 2 N's. Well, this makes it a little bit easier. We'll go ahead and put a 2 here to fix the N. But that also changes our H's, because instead of having 3 H's, we have 2 times 3 is 6, which 2 plus 6 makes 8, and now it's balanced. So this would be our balanced equation. So the steps we have to recognize are we have to find the acid and base. And so this was our base. I'm going to mark it in blue, because we know that bases turn red litmus paper blue. And this is our acid. It starts with an H. And acids turn blue litmus paper red, so I'm marking that one in red. And then once you put them together, you have to figure out what's moving. In this case, here's our H plus that's going to do the moving over that way. And then we have to balance the things. Okay, the next one, it gets a little bit trickier. So we start with H2CrO4, and we put that with AlOH3, and that's going to make, and that's where we have our question. So again, if we recognize that OH is what usually indicates, hey, this must be a base, and this H at the beginning tells us this one's probably our acid, then we can figure out that we need to take this H and move it here. But we have 2 of those H pluses moving, and we have our OHs that are receiving them. We have 3 of them because of this little 3 subscript. So when we have 2 of one thing, let's say we have a bag of something that comes in 2s and a bag of something that comes in 3s. To make it work, we need to get 3 bags of this and 2 bags of this, and in the end we would have 6 of everything, right? Because we would end up with 6 of these, and then we would end up with 6 of these. You can pause and process that if you need to. So what I'm going to do is, I know that I'm going to end up with H2O. The H comes from here. The other H and the O comes from here. And because I plan on using, oops, I just realized I swapped those 2. Let me fix that. Well, I didn't swap them. We have 2. We need to buy 3. We have 3 packs here, so we need to buy 2 3-packs. And altogether, we're going to end up with 6 H2Os. And we can check that and we can see. So for example, let's find a different color. So we have HCrOAl. So on this side, we have 6 H's from here, plus 1 Cr, plus 4 O's, but there's 3 total, so 4 times 3 is 12. And then we have 2 of the Als. And this OH in here means we have more O's and more H's. So we have 3 O's times 2, that's 6. So we have to add 6 more. And then we have 3 H's, because there's a little 3 here, so that means we're buying like a 3-pack of OH. But we bought 2 of them, so 3 times 2 is 6. So we have 6 H's, so that makes 12. And then on the other side, oh, we haven't quite finished the other side. Let's finish. All right. The other things that are left over are the Al and the CrO4. Now, CrO4 is not on page 245. I checked it to see if it was. I can tell it's, because it's going with Al, it's probably an ion. And so this wouldn't be on the test because there's going to be ones that are on your chart or that you have memorized on your test. But you can look it up and see what is CrO4's charge, which is, it says -2. Or the other thing you can do is you can recognize that over here there were 2 H's in this very first thing right here that went with this. We know H has a 1+ charge, and there's nothing like around here with parentheses with like a little number out here on the outside, which means that this one must be where the 2 came from that went here, and the 1 went here. So it's 2-. So I can tell that the CrO4 is probably a 2-, but I looked it up to just be sure. So we have a 2- here, and aluminum is a 3+, and so when we put them together, we have to swap those. So we get a 2 here, and then this has to go in parentheses because the whole thing gets a 3. So now we can count the other side. So we have 6 times 2 is 12 H's, 6 O's, and erase some of our extra stuff up here. So we can see Al, we have 2 of those. The Cr, we have 3 of those. And the O, we have 4, but there's another 3 on the outside, so that's 4 times 3, and that's 12. So when we add that, it makes 18. So if you notice, my numbers check out, except for, oh, this one, I changed this one by putting a 3 in front and forgot to fix it. That one does check out too. So just to be sure again, 6 plus 6 H's, 3 Cr, chromium, which letter is X? O, 12 plus 6, 18, and Al2. And then over here, H's, we have 12, they're all there. Cr, we have 3 on the outside because there's like an imaginary 1 right there. So 1 times 3 makes 3. O, we have 6 plus 12, that's 18, and Al, we have 2. So it balances. So this one was a little bit messier. The things we had to recognize were not only what's our acid and what's our base, but we also, I'm sorry, I'm going to clean up while we're talking here. We have to figure out what's our acid and what's our base, but we also had to figure out how many of our H pluses were moving so that they could go to the other thing, which in this case was the OH, and how many OHs would be receiving them. And so we had to use a little bit of logic to figure out that the things on the left needed a 3 and a 2 for the coefficients, when that may not be quite as obvious when you think about it. And the CrO4, knowing that that was a 2- charge, that's something that wouldn't be on the test. But it's good to see it, so you know that you kind of have to know it sometimes. All right, and then our last one of these types, where all they're asking us to do is still determine the reactions. We're just putting things together. We have H3PO4 and NaOH. All right, so with this one, it's probably, you're probably getting used to it. Can you find the base before I mark it? Base is right here, so there's an OH. Obviously, that means the acid is this one. And our clue could be that there's an H right here at the beginning. In fact, there are 3 H's. So when we go to make our thing, our H's are going to combine with our OH's to make H2O. But we have this little H plus, it's like we have 3 of them that are, all 3 of these want to move to be with this one OH, which means we need 3 of that so that we have enough OHs to receive them. Kind of like the last one, but a little less tricky because we just have to add a coefficient in front of there. And then what are we missing? And I'll add a number in front of here when I'm finished with it. We didn't use the Na yet, and we didn't use the PO4 yet. PO4 is one of our polyatomic ions. That one is on page 245, and that one has a 3- charge. And on our periodic table, Na is in the first column, so it has a 1+ charge, which means when we put those two together, we need to, let me make sure I got that right. Yeah, 3- for the PO4, and Na is in the first column. So when we put them together, the 3 is going to come here, and the 1 would go over here, but we know we have 1, so we don't need to write that 1, okay? So I'm going to erase my charges. That may be the tricky part, is recognizing when you build an equation, you have to figure out what's changing with what, and also how many we need. Now we can look and see how they combine. So we have H's. Oh, that's a really sad looking H. Sorry about that. Let's fix it. Okay, so we have 3 H's plus 3 more over here. That's 6. We have 1 P. We have 4 O's plus another 3 O's over here, so that's 7. And then we have 3 Na's. On this side, we have 2 H's. So we go ahead, and before we count anything else, we know we need to make this bigger. And you probably figured that out from the beginning when I said we were moving 3 H's from here to the OH. So we needed 3 OH's to receive them. So probably going to be making 3 molecules of water if I'm using 3 H's and 3 OH's. So 6. And then O's, we have 3 O's. There's some more down here. So 4 more. That makes 7. And then P's, we just have this 1 P. The 4 is not on the outside of parentheses, so it doesn't affect the P. And then NA's, we have 3 right here. So 6, 1, 7, 3. Everything checks. So this would be our balanced equation. That's our reaction that's happening between those chemicals. Okay, so you have, I think, some on the test that are like that, where you have to match up that. Okay, the next one starts having you do stuff with it. You still have to make an equation, but you're going to have to neutralize something. And they want you to, they give you a solution and another solution. So those are your 2 reactants. A student needs to neutralize 550 milliliters of a 5.6 molarity H2SO4 solution. How many grams of AlOH3 should be used? So we have H2SO4, and we're putting that with AlOH3. These are being neutralized, therefore we're working with acids and bases. So let's go ahead and know that we're going to take this H here and put it with these OHs here. Can you already guess what I'm going to have to do? I have 2 H's that are both going to move and 3 OHs that are going to receive them. I'm going to have 3 of these and 2 of these so that I can end up with 6 H2Os. And then what else is left? I have an Al that I didn't use here and an SO4 that I didn't use there. So I'll put those together. And before I call it good, I need to check. Al is in column 3. SO4 is a polyatomic ion, so I check my chart, unless you got to memorize by now. So SO4 has a 2- charge. Oh, boo. This one's not super awesome because you get to do extra stuff. So 2 there, 3 there. So there we go. So we've got them together, and we've made it work, and it's pretty-ish. I'm going to erase the little things up here so I have more room to write stuff. All right, and then what have they given us, and what do they want? So let's mark what they've given us. They've given us that for the H2SO4, so this first one we have 550.0 milliliters. How about if I just go ahead and move my decimal here and call it liters, because I know that everything is working in liters in these problems. And then it tells us what the molarity is, 5.6 molarity. And then what they want to know is grams of this. This is what we want to know. How much do we need? Well, just like in our experiment last week, we had to mix things until the liquid turned clearish. That means we had to have everything balanced, just like the equation would be. So if we have 3 moles of one and 2 moles of the other, that will work out. So let's change things to moles, because equations work in moles. For this, you'll need to know what your equation is for molarity. So M equals total moles per liter. So they've given us the liters and the molarity. So they've given us 5.6 equals moles over 0.5500 liters. So if we just take this number, multiply both sides by 5500 liters, we'll figure out how many moles we have of the H2SO4. So let's see, let's pull up a calculator. Not right in front of where I'm working though. All right, so 5.6 times 0.5500, and I get 3.08. So I can keep 2 of those digits. So because of the 5.6, I'm going to call it 3.1. So I have 3.1 moles of this, which means that I can now figure out how many moles of the next one. I'm going to write this next one under because I have enough room to write it. So if I have 3 moles of this and 2 moles of this, let's set it up sort of like a ratio. We can do it a different way, but I think this will make more sense to those of you who like ratios. So of the H2SO4, it's 3 of those makes 2 of the AlOH3. In other words, to get from here to here, we would need to divide by 3, and then we can multiply by 2. So we're going to do the same thing this way. We're going to take our 3.1 and divide by 3, and then multiply by 2. And I have to clear this out because I don't want it to say 3.8 because I want the rounded number. So divide by 3, and then time, oh shoot, I didn't put the divide symbol. Clear 3.1 divide by 3 times 2. And I could only keep 2 significant figures, so it's going to be 2.1. So I'll have 2.1 moles. Well, at this point, it becomes something that you've done before. This is a little messy, sorry about that. We can change moles to grams. We just need to know what the molar mass of AlOH3 is. So let's put that, I'll use brown and we'll put it up here. So the molar mass would be, for 1 mole of that, it would equal, so Al is 26.98, plus we have 3 O's, so that's 16 times 3, and we have 3 H's, so that's 1.01 times 3. If we put all that in our calculator, we'll figure out what the molar mass is of that. Delete. Okay, so 26.98 plus 16 times 3 is 48, plus 1.03, that thing equals 3.03, so we have 78.01. So 1 mole equals 78.01 grams. So if we want to change 2.1 moles to grams, moles goes on the bottom, grams goes on top, and then we just put in that number we just found. Why did I write it to? 78.01, and then we just multiply. So 78.01 times 2.1. And remember, we can only keep 2 digits because 2.1 has 2, so we can't call it 163 or 163.8. It's just going to have to be the 1 and the 6 and then 0, so 160. So the answer to this one is 160 grams. I'm so sorry this is neat. I mean, not neat. I just ran out of room. The process was that we made an equation, we labeled what we knew, and then we figured out how to get there. With all of these things, we're going to be using this little equation over and over. So make sure that you think almost in every problem that you have to do on the test, how can I fit that in? Because it's pretty much going to be on all the problems. All right, the next one says 115 milliliters of a solution of that, of unknown concentration, so we don't know the number that comes right before that capital M, is titrated with a 2.16 molarity solution of another thing. If it takes 7.18 milliliters of the second thing to reach the endpoint, was the concentration of the first thing. So again, we're going to start by setting up an equation. So this is the thing that we're titrating with this thing. So let's go ahead and write those together. Can you see which one is your base and which one is your acid and how to put the next ones in? If you do, go ahead and write it and then check the board and see if you got it right. Okay, so the H on the first one, that would be our acid. It's running to the NaOH, or rather to the OH part of the NaOH. So the H at the beginning here and the OH here are coming together to make your H2O. And then everything else is going to come together to make the NaClO3 at the end. Now the ClO3, I think, is another one that is a, yeah, we don't have that one as one of our things. This right here, because the H is a 1, if this had had any kind of charge, it would have been right here, because the H is a 1 plus, and this would have had whatever minus, and that number would have ended up down here. And because that didn't happen, you can just know that this would be a 1 minus, and Na is 1 plus. So you're good to just leave it like that. Again, I'm not going to have one on the test that you don't already know or have on your chart. And you could also look it up. All right, let's check and make sure we got everything lined up. We have 2 H's on the left, 2 H's on the right. 1 Cl on the left, 1 Cl on the right. 4 O's on the left. 1 plus 3, 4 O's on the right. 1 Na, 1 Na. So everything lines up, so we're fine. We're good to go. All right, so for this one, what do we know? We know that we have 115 milliliters of this one. Let's go ahead and just put that in liters. I'm going to keep my 0 because it's significant. And then it tells us 2.16 molarity of this other one. I'm going to put my 2.16 M a little bit lower so that my liters can stay lined up. And then it tells me how many liters I used of the NaOH. I'm going to change the milliliters to liters, so I have to move this decimal 1, 2, 3 spaces. So 0. I have 2 bumps and then 718 liters. And then those liters work out to make it reach its endpoint. In other words, the reaction's complete, nothing's left over. They stop there, and they want to know the concentration. So what they're asking for is, what is my molarity? What is the thing that goes here? Well, to do that, I can tell that I have used 1 mole of this and 1 mole of this. So as long as I can find the moles that I used of one, I can use that to find the moles of the other, and then find the molarity. So if I know how many moles this 7.18 milliliters is, then I can move that into moles, and then I can figure out this would have the same number of moles because they both have a 1 coefficient, and then I can use moles and liters in my molarity equation to find the molarity that I want. So that's my plan. So let's start with that. So let's start with our base because we have all the information we need. So M equals moles over liters. Again, I'm trying to find moles, so I'm going to rearrange this. I'm going to say moles equals M times L. So my M is 2.16 and my L is 0.00718 liters. I'm going to multiply those two together, and okay, that's actually going to take me too long. I'm going to try to hurry. I'm running out of time. All right, when I put it on my calculator on my phone, I got that. I can't keep, oh, actually I can keep all those numbers. That's awesome. All right. And because these are both like having 1s here, I know that I also have the same number of moles of this if they had a complete reaction. And now I can use, I probably should have written that one in red. Now I can use my moles per liter to find molarity. So 0.0155 moles per the liters that I have. And when I put those two in, just imagine I use my calculator. You can pause it and try using your calculator if you want. That's what I get. That's what we go right here in this section is 0.135. And you only have, oh shoot, I didn't mean to put that dot there. You only have 3 significant digits in the 0.0155, so that's why I can only keep 3. All right, moving on. The next one says concentrated acetic acid is 17.4 molarity. How would you make 750 milliliters of a 1.5 molarity acetic acid solution from concentrated acetic acid? Notice that the only thing we said over and over was acetic acid. We don't need to make an equation. Yay, everybody celebrate, because we only have one thing. And that one thing, they've told us what it is. So here's the concentrated version. The concentrated version is 17.4 molarity. And what they want is they want to have 750 milliliters, and they want it to be 1.5 molarity. Well, this is way too concentrated, right? So what we need to figure out is how much of it do we use? We scoop out some. That some that we scoop out will have a certain number of moles. We add enough water to make it be 750 milliliters. And then because the 1.5 molarity comes from the moles divided by liters, all we have to do is make sure we scoop out the right number of moles from the concentrated version. So to do that, we want 1.5 molarity, and remember, M is moles over liters. And so we need some number of moles to go with our, let's go ahead and change, oh, just kidding. Yay, they already gave it to, no, just kidding, that is milliliters. I was thinking it was liters for a second. All right, there we go. So if we use this equation, we can figure out how many moles our final thing should have, our non-concentrated version. So if we multiply 1.5 times 0.7500, then we will get, oh, did I do this already in my calculator? We will get 1.1 moles. So I need 1.1 moles of this stuff over here. So how do I get 1.1 moles? Well, same thing. This is M equals moles per liter. That means I can figure out if I only want 1.1 moles, I can take the molarity, multiply it by the liters, and figure out what it is. Basically, I just left my liters blank this time. I took this equation, plugged in stuff for moles, plugged in stuff for molarity. I went ahead and started rearranging it so that I could end up with my liters by itself. This is molarity. And that will tell me how many liters of this stuff I need to use so that I can get the right number of moles. So in this case, it would be 0. If you put this in your calculator, you get 0.063. You might get a bigger number than that, but you can only keep, not bigger, but like a more specific, really long decimal. You can only keep 2 significant digits. So you would need to use, you can either leave it like that, or you could say, I need 63 milliliters, if you want to change it back to milliliters, plus enough water, because you're diluting it down to be a lower amount, to make 750 milliliters. All right, so that one, you just use the same equation twice. At this point, we've reached about the 30-minute mark, so you're probably done with co-op. We're probably done with class. My timer actually says 28 minutes at this point. So if you want to come back to this later, I'm going to work some more problems that are helpful. Or if you want, you can just never come back to this video again and just rewatch the first one, or say I got it and move on. For those of you who want to continue, rewatch this video, start at the 28-minute mark, and we're going to keep moving forward. All right, so the next one says, and this one comes from number, I should have left the numbers up because I can't tell. What volume of a 0.75 molarity solution of HCl would be required to neutralize 250 milliliters of a 0.01 molarity solution of CaOH2? So that is, if you're doing the extra problems and you've downloaded them, this is number 4 on the extra problems. And I'm probably going to keep using my calculation sheet that I worked these on paper, so I'm just going to skip doing the calculator and assume you know how to use your calculator to make this video faster. So this one's kind of like the other ones. We're going to have to start by making an equation. I'm going to go ahead and put HCl in red because I can tell that that's my acid. And then I'm going to put CaOH2 in blue because I know that's my base. To do this, I'm going to end up with H2O and CaCl. You probably recognize that one really easily from our ionic, oh, I suddenly can't think of the word, combination things, whatever. So Ca is +2, and Cl is 1 minus. So this is going to have a 2 here. And the Ca will not have a 1 because we just don't write that. All right, so looking at our equation here, we have 2 OHs that we used over here, and we put 1 water with them. So 1 H with them. So we really need to have a 2 here to give us 2 of these. And I figured that out from this 2 right here. I need to have 2 of these to go with the 2 here. Oh, and that will produce the 2 here that I accidentally just erased. Let's check stuff just to make sure. So we have H, we have 2 plus 2, and on the other side we have 4. For Cl we have 2, and we have a 2. For Ca we have 1, and we have 1, and for O we have 2 and 2. So everything balances. I'm not going to keep these numbers. They're just to check. So always check and make sure yours is balanced before you move forward. Now I'm going to write in what I have. So they told me that I have a 0.75 molarity solution of this, and they want to know the volume. What volume of that? So what volume of that would be required to neutralize? And they've given me 250 milliliters. I'm going to put the decimal there and call it liters. And then they've also given me that I have a 0.010 molarity. All right, so because I know this and this, I can use those in my equation. Remember, M equals moles per liter. So if I want the moles, I'm going to multiply the M times the L. So 0.010 times 0.2500. This has 4 significant digits. This one has 2, so I can only keep 2. And the answer to this will tell me how many moles I have. I put it in my calculator, hopefully somewhere. Yes, I did. And I got 0.0025. Oh, that should have been a little bit more obvious. So I have 0.0025 moles of this. This is my just kind of scratch area. Because I have that, I have 1 as an invisible coefficient there, and I have a 2 here, which means that if I multiply this number times 2, I can figure out how many moles. Yes, let me change colors. I can figure out how many moles of the HCl I have. And then I know the molarity I want, so I just put those in my equation to find the liters I need to make that molarity. So this number times 2, 25 times 2 is 50, so 0.50. And these 2 are both significant, but the other zeros are not. So now we just put it in the same equation. I'm going to put my work back over here. So I want liters, so I'm going to rearrange this and switch the M and the L. So I have liters equals moles divided by molarity. If that's confusing, that's kind of an algebra thing that you should have gotten to by now in the year if you're taking algebra currently, but you can multiply both sides by an L and then divide both sides by an M to show that switching these 2 makes sense. So I have 0.0050 moles divided by the 0.075 molarity that I want. And when I do that, I get 0.0067 liters. So I could erase the, well, actually, let me leave the question mark there so you can see what I have. So this will be my answer. You could also change this back to milliliters by saying 6.7 milliliters. That would also be okay. Those are the same thing. All right, this next one is number 7. If you download the extra problems from online, it says a 1.3 molarity solution of something is used to titrate 15 milliliters of another solution. Awesome. That means we have to make an equation. This one's a little bit harder to balance than some of the others that we've done. And then it tells us how many milliliters we use of the acid. So in this case, we have to even know which one's the acid because they're not telling us. And they want to know the concentration of the base. So let's start. So these are our 2 things. Let's see. This one has an OH, so that's our base. And this one has an H at the beginning, so that's our acid. So let's go ahead and write H2SO4 plus KOH. And then what does that produce? Well, we can see that our H over here, we have 2 of them, is going to go with our OHs here to make H2O. We only have 1 OH, but we have 2 H's. Let's just go ahead and know that we're probably going to need a 2 there. And then our K is going to go with our SO4. This one has, let's see, K is in our first column, so that's our 1 plus. And then SO4 is one of the polyatomic ions on page 245. It has a 2 minus charge. So when you switch those two, you get a 2 here and a 1 there. Let's check our things. So we have H's, we have S's, we have O's, we have K's. So over here we have 2, 1, 4, 2, we have another O, and we have, oh, just kidding, we have 2 more O's. What is wrong with me? That's 2. And we have 2 more H's. Why did I write that on the S row? I don't know. And then on this side, we have 2 here, and S's we have 1, and O's we have 1 here, and 4 here for a total of 5. And then we have K's, we have 2 K's. So that kind of breaks it a little bit. Let's add a 2 here. Now we have 4, so that fixes that. But we now have 2 O's plus 4 O's, which is 6 O's, which breaks it. And so, actually, no, it doesn't break it. I just can't add. I can do chemistry, but adding is hard. There we go. All right, 4, 1, I'm just rechecking, making sure I got it right. 6 O's, and 2 K's, and then this side I just checked, so we're good. Awesome. All right, so we're going to erase all of these. Now that we've balanced it, we don't need to see how we balanced it or what our records were. I mean, if you're working on paper, you kind of do, because you can't really erase as quickly. All right, so now that we know that, let's fill in the rest of the stuff. So it tells us the molarity of the first solution. So let's go ahead and write that down, 1.34 molarity. It tells us it's used to titrate 15 milliliters of another solution. So we can go ahead and put that. Let's just go ahead and move that decimal 1, 2, 3. Put that in liters. And then it tells us it takes 17.8 milliliters of acid. All right, so I guess you really don't have to know which one's the acid because the other one already was given in milliliters, so you can kind of know. But we can go ahead and change this to liters. 1, 2, 3. So I have a 0, 1, 7, and the 8's still there. And that's how far it is to reach the endpoint. And what they want to know is what is the concentration of the base. The concentration is the molarity. So they want to know, what is this? Well, that's not too bad because, again, we're just trying to find, we're in an equation, we got to work with moles. So we're going to do the same thing. What is the equation I'm working with? Let's say it together. M equals moles over liters. And so because we want moles, we're going to multiply both sides by liters, get rid of that, and so we can just have moles equals liters times molarity. So if we multiply the liters, the 0.0178 times the 1.3 molarity, the answer to those two multiplied will give us the number of moles that we have. So we get, I already did this in my calculator, 0.239. And we get to keep 3 digits, so that's why it's rounded to the 9. And then to go from here to here, we have 1 mole here and 2 moles of the KOH in our equation. So we need to multiply that number by 2, and that will give us how many moles of KOH we must have used. 7, 8. And then we can do the same thing that we did using our M equals moles over liters. But this time, this is the thing we actually want, so we're not going to rearrange it. So we would take our moles, and we would divide by the liters. And we do that. Oh, I should have written all this in blue. Let's just box it in blue. When we get that, that gives us the question mark that we're going for. So when we divide those two, we get, let's make a, oh, this is going to erase my whole box. We'll just make a mark like this. When we divide those, we get 3.19 molarity. So that's our answer. That's what goes in this box right here, is 3.19. And all we did was we set up an equation, we balanced the equation, we used things we knew about acids and bases and ionic formulas to do that, and then we just used our molarity formula several times to process this. All right, the next one says a chemist makes 50 milliliters of an acetic acid solution with a concentration of 5 molarity. A student wants to use that to make a 1.5 molarity solution. What volume of 1.5 molarity solution can he make if he uses all of the original solution? This one's number 9 from the extra problems. And if you notice, we're talking about acetic acid and nothing else. So we don't have to set up a formula for this. So actually, let's use red since we're talking about acids. So 50.0 milliliters, or in other words, 0.0500 liters, and the concentration is 5.0 molarity. We want to use this. This is what we have, what they've made. We want to use that to make something new. What we want is we want a 1.5 molarity solution, and we need to know what volume. So how many liters do we need, or can we make? So if we use all of this, we're going to use all of this right here to make it. In other words, we're going to use all of those liters. So let's figure out, again, we're using the same thing, M equals moles per liter. The thing that we don't know is how many moles of acetic acid is in this 50 milliliters that we have, this concentrated solution. So if we take our moles, M times L, so we take the 5.0, my pen stopped writing. What on earth? Okay, I'm going to have to use my finger. It's going to be less pretty. Oh, that's, well, see if plugging in, oh, good, plugging in for a second renewed it. Times 0.0500 liters. If we do those, we will get 0.25 moles. So that's all the moles we have in this original solution. I'm going to put this box in green and switch over to green. So we have possible 0.25 moles that we can use. And in total, we're using all the solutions, so we're using all of those moles. So we can do the same thing. We can take our M equals, actually let me erase that. I'm going to put it up here. We're going to take this same formula up here. We want the liters. We want this. So we're going to just switch it and say liters equals moles over M. We can plug in our 0.25 moles that we have. Plug in the M we have. And then when we put that into our calculator and divide 0.25 divided by 1.5, and we keep 2 decimal places, we end up with 0.17 liters. 0.17 liters. And we could change that back to milliliters if we wanted. We could say that we're going to use 170 milliliters, but it didn't ask us to put in milliliters, so sometimes it's usually safer just to leave it just like it is in whatever unit you found it if it doesn't tell you. All right, a chemistry student takes 50 milliliters of, that's just, well, yeah, of a sodium hydroxide solution and dilutes it so it now has a volume of 250 milliliters. He then titrates that 250 milliliter solution to find it is 1.7 molarity. What was the concentration of the original? This is number 10 on the extra practice problems, and this is our last one. So again, we're only talking about one thing. We are only talking about this right here, the NaOH. Let's see what we're starting with. Let's do like start or original. Let's call it original because that's how they have it. And then we'll call it diluted. That way we can keep straight our information. Diluted. So we had 50.0 milliliters, or in other words, that many liters. And we diluted it, and so now it is, let's change to a different shade of blue. We now have 250. That looks exactly the same. That is not helpful. Let's use orange this time. So we have 250 milliliters, or we could say 0.250 liters. That's our new amount. And then we titrate this. In other words, we mix this base, this diluted base, with an acid until we get to that point where the color's changed, and so we know that we've hit the endpoint, we've neutralized it, and we use whatever we're neutralizing it with. We already know the stuff of that. This is kind of like the math we did in our experiment 11.3. So we already know the molarity of the thing, so it helps us find the molarity of this thing. So we don't have to do the math. They're just telling us. We figured it out, and it's 1.7 molarity. That's what the diluted formula is. What they want to know is, what is the original? What molarity was this one? Just like we've been doing before, we just take our formula. M equals moles per liter, because we can use the molarity and the liter, and we can find how many moles this had. And then because we know that all these moles came from the original, because we used all of the original, it just says we took 50 milliliters and diluted it. So whatever moles we have in the diluted version, we had that same number of moles in the original. We just didn't have as much water diluting this stuff. So let's take moles equals M times L, 1.7 times 0.250 liters, and our moles that are in the diluted amount are 1 to 2.5. Where did I write that down? Did I not write that one down? Oh, yes, I did. 0.43. That's how many moles I have, which means that must be the same number of moles I started with. I must have had 0.43 moles in this. It was just, there was less water, so it was more concentrated. Knowing that, though, I can find the molarity. I can take the 0.43 moles that I've always had, and I can take the number of liters that it was in, and I can divide those to find the molarity. So 0.43 moles divided by 0.0500 liters gives me 8.6 molarity. So that's the original. Again, all I did was outlined up my information to keep it all straight, and then I just used that molarity formula over and over. Now, if you had gotten a number instead of 8.6, if you had divided wrong and you got a number less than 1.7, that should have triggered something, because the original formula, non-diluted, or the concentrated version, should always have a higher molarity because it's more highly concentrated. All right, I have left space in case you want to go back and practice any of these. You can also review the Kahoot game we played. I put that on here. So as you go back through, you can check these out. So there's space to look at it. You can write it on paper. If you know how to write on a PDF, you can do it on that. And then you can go back and check and see if your answers match my answers. My answers are a little messy because writing on a computer is harder than it looks. But every page has a try it, where you can go back and try it, and then the answer. Try it, answer, all the way through, including the ones that we didn't work in class. Okay, good luck studying for your tests. You can call me or text me if you have questions. I'll be driving today about 11:30, but before that, I'll probably just be sitting and waiting. And